We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will begin our study of oscillatory motion. Our primary example will be that of a mass attached to one end of a spring whose other end is fixed. This system oscillates about its equilibrium position with a frequency that is determined from the spring constant and the mass of the object. This motion is called simple harmonic motion. We will also offer an alternative description of this motion that makes clear its strong connection to uniform circular motion. We will determine the time dependence of the displacement, velocity, and acceleration of the object by applying Newton's second law to the system. We will find that all these quantities can be written in terms of sines and cosines whose argument is the product of the angular frequency of the oscillations and the time. Finally, we will demonstrate a procedure for obtaining the amplitude and the phase of these oscillations. Here we see a mass that is free to move along a one-dimensional, horizontal, frictionless track. The mass is attached to one end of a spring, and the other end of the spring is fixed to the wall. We define x equals 0 at the equilibrium position of the spring. If we displace the mass from this equilibrium position and release it, the mass oscillates about x equals 0. Since the spring force is conservative and the only force that does work on the mass, we know the total mechanical energy of the system will be conserved. That is, the sum of the kinetic energy of the mass and the potential energy of the spring will be the same at any point of the motion. In particular, since the kinetic energy of the mass is 0 at the endpoints of the system, the potential energy of the spring will be maximum at those points. Similarly, since the potential energy of the spring is minimum at its equilibrium length, the kinetic energy of the mass will be a maximum at this point. As the mass oscillates, it continuously trades potential energy for kinetic energy. On the next slide, we will use Newton's second law to build the quantitative description of this simple harmonic motion. Before moving on, though, we need to make one important point. Back when we first discussed the potential energy of a spring, we showed that the potential energy function for a mass on a vertical spring is identical to that for a mass on a horizontal spring as long as we measure displacements from the equilibrium length of the spring with the mass attached. Therefore, everything we have said on this slide so far and everything we are about to prove will be equally true for both horizontal and vertical systems. Okay. Here we see the horizontal mass plus spring system we discussed on the previous slide. At any displacement, we know the force, and therefore the acceleration of the mass. What we do not know yet is the behavior of the system as a function of time. The problem here is that the net force, and therefore the acceleration, is not a constant. So we cannot simply use our kinematic equations for constant acceleration. Instead, we will need to write Newton's second law as a differential equation and solve for the displacement as a function of time. We can write Newton's second law explicitly in terms of the displacement by remembering that the acceleration is defined to be the time rate of change of the velocity, and the velocity is defined to be the time rate of change of the displacement. Therefore, Newton's second law for a mass on a spring can be written in terms of the displacement of the mass and the second time derivative of this displacement. This equation is called a differential equation for the displacement. To solve it, we need to find a function, x of t, which when differentiated twice gives back the negative of the same function, x of t, multiplied by a constant. It is convenient to define a quantity omega squared as the ratio of the spring constant to the mass. We can solve this equation by inspection. Now, that's the mathematician's word for guessing. Namely, we know that if you differentiate the sine of an angle, you get the cosine of that angle, and differentiating once more gives you minus the sine of the angle. We get a similar result for differentiating the cosine of an angle twice. Therefore, we expect that our solution will involve sines and cosines. For example, if we assume x of t is equal to a times the sine of omega t, we find that the second derivative of x of t is just equal to minus omega squared times x of t. Similarly, we find that x of t equals b times the cosine of omega t is also a solution to the equation. Indeed, any function that is a linear combination of sine of omega t and cosine of omega t will be a solution to our differential equation. Before discussing the physical meaning of this solution, we will make a slight digression to review some properties of sines and cosines on the next slide. Here we see a sinusoidally oscillating function whose vertical axis represents the displacement of the mass and spring system as a function of time. If you were asked, is this a sine or a cosine, all you would be able to answer is yes. There is no difference in the overall form of a sine function and a cosine function. Both oscillate symmetrically between +1 and -1 with a frequency determined by their argument. And both functions repeat after their arguments increase by 2 pi. It's not until we decide where to place t equals 0 on the plot that the actual distinction between a sine or a cosine can be made. Indeed, if we start with a cosine function and we slide the t equals 0 point to the left by pi over 2, it becomes a sine function. This connection between sines and cosines can also be understood geometrically. Here we see an object in uniform circular motion with radius r centered on the origin in the xy plane. The angular displacement at any time t is given by the product of the time and the angular velocity. To find the x and y coordinates of the object at any time, we take the projections of the radius vector along the appropriate axis. Consequently, we can understand the cosine and sine functions having identical shapes shifted by 90 degrees relative to each other simply in terms of the 90-degree separation of the x and y axes. This picture also explains why we use the term angular velocity to describe the oscillation frequency of an object executing simple harmonic motion. The displacement of the oscillating object from equilibrium is literally equivalent to the projection along a single axis of a particle moving in a circle with angular velocity omega. The two descriptions of the motion are just two sides of the same coin. The most general form for a sinusoidal function having frequency omega can be written in terms of two constants, an amplitude, which is the magnitude of the maximum displacement, and a phase angle phi that allows the maxima to occur at some time other than at t equals 0. In the geometric picture, the amplitude corresponds to the radius of the circular motion, and the phase angle corresponds to the initial angular displacement. This function repeats after its argument changes by 2 pi, which corresponds to a change in time equal to 2 pi over omega. We call this time the period of the oscillation and denote it by a capital T. We are now in a position to finish the example we started 2 slides ago. Here we see the mass given a displacement plus d and released from rest at time t equals 0. Our task is to determine the position of the mass as a function of time. We know the differential equation describing the oscillation of the mass has a general solution of the form shown. We can determine the angular velocity since we know the spring constant and the mass. The remaining parameters, a and phi, are determined from the initial conditions. Since the mass was released from rest, we know from energy conservation that the displacement can never be larger than d. Consequently, the amplitude A is just equal to d. Further, since the initial displacement is equal to plus d, we know the cosine phi must be equal to 1. Therefore, we take phi to be equal to 0. We have now arrived at our solution. a function that determines the displacement as a function of time. We can obtain the velocity as a function of time by simply differentiating this function with respect to time. One more differentiation gives the acceleration as a function of time. It is evident from these expressions that the velocity of the object is zero when its acceleration is maximum and vice versa. Note that the factor multiplying the sine or the cosine in these expressions for the velocity and acceleration is the maximum possible value for these quantities. Let's plug in some numbers to get a feeling for these quantities. If we take the mass to be 2 kilograms, the spring constant to be 8 newtons per meter, and the initial displacement to be a half a meter, we obtain an angular velocity of 2 radians per second, corresponding to a period of 3.14 seconds. In other words, it takes a bit over 3 seconds for the object to make one complete oscillation. Multiplying the angular velocity by the amplitude, we find the maximum velocity will be 1 meter per second. While multiplying the square of the angular velocity by the amplitude, we find that the maximum acceleration will be 2 meters per second squared. In the last problem, we saw that the angular velocity, and therefore the period of the motion, was determined by the physical parameters of the system, the spring constant and the mass. To complete the description of the motion, though, we also needed to determine the amplitude and phase of the oscillations. These parameters were determined by the specification of the initial conditions, namely that the mass was released from rest from an initial displacement. We chose those initial conditions in order to simplify the determination of the amplitude and the phase. We will now do another example with different initial conditions to illustrate the general procedure for determining these quantities. Here we see a mass oscillating on a spring, just as in the previous example. But we will not start the system from rest at a maximum displacement. Instead, we see that at t equals 0, the displacement of the mass is x naught and its velocity is v naught. How do we go about determining the amplitude and the phase of the oscillations? Well, we can start from our general expressions for the displacement and velocity as a function of time and evaluate them at t equals 0. We now have two equations that we can solve simultaneously for the amplitude and the phase. In this example, we can divide the first equation by the second to find an expression for phi, and once we know phi, we can use either of the two equations to solve for a. In this example, we have demonstrated a general procedure for determining the amplitude and phase of the oscillations. Using these parameters, we can obtain values for the displacement, velocity, and acceleration of the oscillating mass at any time. Of course, many important parameters of the motion, for example the oscillation frequency and the energy in the system, are not time-dependent and can be determined without any knowledge of the phase. One of the most important properties of simple harmonic motion in mechanics is that the frequency of the oscillations is determined totally by the constants needed to describe the net force that acts on the object. For example, in the spring plus mass system we have just studied, the frequency was determined from the spring constant and the mass. Therefore, we see that the frequency of the oscillations does not depend on how the oscillations were started. For example, if we double the amplitude of the oscillations, thereby making the mass travel twice as far during every cycle, the time taken to complete that cycle is still exactly the same as it was when the amplitude was small. This interesting property is a consequence of the fact that applying Newton's second law for this example results in the acceleration, the second derivative of the displacement with respect to time, being equal to the product of a negative constant and the displacement. Anytime we find such an equation, we know we can write the solution in terms of sines and cosines with an oscillation frequency determined from the value of that negative constant. In our example, the negative sign came about because the force was a restoring force. The force always acted in such a direction so as to restore the system to its equilibrium position. As we shall show next time, other systems having a linear restoring force, such as a pendulum under certain conditions, will also undergo simple harmonic motion. We conclude with a brief discussion of the main points of this prelecture. First, we discussed our primary example of simple harmonic motion, namely, the motion of a mass attached to one end of a spring whose other end is fixed. The net force acting on the system is proportional to the displacement of the mass from its equilibrium position. This restoring force produces oscillations about the equilibrium position of the system. Applying Newton's second law, we determined the angular velocity of these oscillations is equal to the square root of the spring constant divided by the mass. The explicit time dependence of the displacement, velocity, and acceleration of the mass can be written in terms of the sine and or the cosine of an angle given by the product of the angular velocity and the time. Second, we found that the amplitude and the phase of the oscillations must be determined from the initial conditions, a specification of how the oscillation got started. In particular, the amplitude is determined by the initial energy put into the system, and the phase is determined by our definition of t equals 0. Third, we demonstrated that simple harmonic motion, specified by an angular velocity omega and an amplitude a, can also be represented as the projection of an object moving in a circular path of radius a with constant angular velocity omega along an axis that passes through the center of the circle.